3. Here we go. All right, so for our warm-up here, we have the ddx. What does that mean, ddx in front? Take the derivative of what follows with respect to x, right? Yeah. The only rule that we know right now are the power rule and the sine and cosine rule. Pretty salty. So we have to make it term, and every term has to have the form either ax to the n or a sine and cosine in it. I don't see any sine and cosines here, but I do not see term. So we have to expand this out first. Now, when we expand it out, listen, Bendelay, because I've already noticed several things wrong with yours.
Yeah, I know. That's why
when we work straight down, we need to put the ddx each time. Okay? Now, when we expand, we have to expand a quadratic. Can we just square the first and square the last? Is that how we square quadratic binomials? No. You either go off to the side and FOIL it, or you're going to get, speaking of double, square multiply double square. Square multiply double square. Square the first and get 9. Multiply them and get negative 6x cubed. Double it and get negative 12x cubed. And then you square the last and you get positive 4x to the 6th. Okay? That middle term you don't want to leave out. Or the ddx. Is that right? Yeah. When you square something, you double the exponent. All right. Now I'm putting ddx again because I'm not ready to take the derivative, and I distribute. So negative 36x squared plus 48x to the 5th minus 16x to the 8th. So when I'm making out the key and I'm coming up with other answer choices, one of them is missing this term, right? Like Jackson. I'm just going to volunteer Jackson. Not that he did it, but like if Jackson were to miss this term when he FOILed it, I would have an answer choice for him. Another thing that I might do here is when you're distributing, 6 plus 2 is 8, but some people might want to multiply 6 times 2 and put 12. So I might have an answer choice of 12 there, right? Now it's in ready to go format, right? And because the ddx is still in front, we're going to get full credit. And we know that we still, bless you, have to take the derivative, which now we're ready to do. When you take the derivative, the ddx goes away. So you multiply and subtract. So you get negative 72, x to the first, plus, ooh, what's this going to be? 40, 24, 240, x to the 4th, and then minus, holy cow, right? 8 carry the 4, so 128, x to the 7th. Jiminy crickets. And there it is, I believe, right? Yeah, that's the answer. And the reason the ddx goes away is because, remember, each of these terms is technically getting a dx. We're taking the derivative of the x variable with respect to x. And guess what dx divided by dx is? It's 1. So essentially, that's why it goes away. Yes, sir.
Is this one we should expect on the test?
Well, you will have one on the test where you're going to have to expand it. Yes, for sure. Numbers that big? Well, you can maybe go off to the side, right? Right? If you had, yeah, good time, old school math, right? 16 times 8, right? That's kind of nostalgic. Yeah. I won't make the numbers that big. I tried to keep the numbers small in this one, but they got a little out of hand. All right. Yeah, we'll get back to the calculator section. All right, so now that we're all nice and warm, let's mosey on to part C, g of x. It's 2 sine of x half cosine of x halves. Now, you're looking at this, and there's a couple of things that are problematic with it. If we're trying to find g prime, the derivative, first of all, we have a product of sine and cosine. We know how to take the derivative of sine of x and cosine of x, but not the product of the two. So the product of the two is a problem. The other thing that's a problem is, notice these are not just sine and cosine of x. The angles are all tweaked, right? X halves, x halves. Yeah, so that doesn't work for us either. So is there a way to solve both of those problems at once? Maybe. When it comes to trig, we have a whole arsenal of mathematical synonyms, right? We have a mathematical thesaurus that we can reference. right? And it's called the Big Book of Trig Identities.
Does that book ever go away?
No, it never goes away. It's always right there. So we're going to go through that book and we're going to see, is there a page that has this on it that's equal to something else? And the answer is yes. All right. So let's review the double angle identities. You need to know these. The double angle identity for sine of 2x, double angle, right, twice as big, is 2 sine of 1x, cosine of 1x. And the double angle identity for cosine is the one that looks like Papa Pid, except it's a subtraction instead of an addition. Alphabetical order, cosine before sine, Papa Pid is plus, the double angle for cosine of 2x is minus, okay? So that has 2 terms and sine of 2x is 1 term. But it expresses both of them in terms of the single angle. Now, this is not an exact match, but it looks a lot closer to which one? The first one, okay? Now, remember, this is what's cool. This x is a variable, isn't it? I mean, it could be anything. It could be 2 sine of pink elephant, cosine of pink elephant. It could be 2 sine of 4b times cosine of 4b. Could it even be 2 sine of x halves, x halves? Yeah. Okay, so notice that most of the time we're probably using the identities in this direction, okay? But in this case, we're using the identity this way. So when we use it that way, here's what we do. Whatever x is, when I call it sine of 2x, I just need to make sure I double whatever this is, yes? So 2 sine of blob, cosine of blob, if you will, is equal to sine of twice the blob. It's a good way to say it. So let's see if we can rewrite g of x with that. 2 sine of blob, cosine of blob, is equal to sine of 2 times the blob. And what's our blob? X over 2. And notice I use an asterisk for a multiplication symbol because I knew how to multiply, but I wanted to draw attention to it as well. I don't know if that works. That's how you calculate it. I better put a dot here. Now, of course, what is 2 times x halves? X. So, oh my gosh, look at that. G of x is really just our old friend Sahala. All right. I know. I didn't recognize it because when I Sahalaed, it didn't Sahala back. And I guess he was trying to be incognito. He didn't want to be recognized. So are we done with the problem? We identified it as sine. Hey, guess what? We're not done with the problem. In fact, the problem now just begins. What is the derivative of 2 sine of x halves times cosine of x halves? Well, it's just the derivative of sine, which is positive cosine. Right. Remember, if it has a co in its name, it becomes negative. Always. If it doesn't have a co, yeah, if you want to say you hate covert ops, whatever, covert is negative. Right? Covert ops are so sus. Right? Wow. That got a reaction. Okay. Just try to make it memorable, right? Try to make it memorable so it sticks. Okay, all right. Any comments or questions on okay. All right. I don't know why we missed that one back in the day, but we went back to it. Okay. So to pick up where we left off on 11, we graphed sine, and we were looking at the slopes and how the slopes at any given point of sine give you the cosine values, okay? Now, what we were going to verify is the slope, and let me draw the tangent line. The slope of sine right here, we said that the slope at 0 was 1, right? And how do we know it's 1? Because cosine only goes up to 1, yes? And then right here, we were guessing, I'm on the graph, I'm on the wrong graph. Right here, the slope of sine at pi, we said was -1. And we knew that because the graph of cosine goes to -1. So what I want to do is verify that. So let's go ahead and find the derivative of sine at 0. Find the slope of the graph of f, which is the blue graph, at 0. Well, when it says slope of the graph at 0, you have to know what to do. Slope of the graph at 0 means slope at a point. What's another name for slope at a point? Slope at a point? Derivative. Good. So I'm after f prime of 0, but before I can find f prime of 0, I need to find f prime of x. So if we got sine of x, then of course it's cosine of x. We just did that. And now to plug in a 0, we do it on both sides. F prime of 0 is cosine of 0. And of course, everyone knows cosine of 0 is what? 1. 1. Okay? So yes, the graph of sine launches out of the origin at a slope of 1. Okay? And that's why the cosine value is in fact 1 there. Now this is a good way to confirm also what I told y'all back in the day when we were doing the limits as x goes to 0 of sine of x over x and tangent of x over x. Because remember I said near 0, tangent of x and sine of x behave the same way, don't they? Here would be sine of x. And then tangent of x curves the other way. It curves like this. That's tangent of x. But remember, in the neighborhood of 0, if you were to keep zooming in, they would behave the same way. And you know why they behave the same way? Not only do they both pass through the origin, but guess what the slope of both of them is at 0? 1. Yeah. Tangent launches out at a slope of 1. And you'll learn that later when we learn the derivative of tangent. And sine launches out of the origin at a slope of 1. So they behave the same way near 0. And that's why when we have the limit as x goes to 0 of sine of x over x, that's going to be the same as the limit as x goes to 0 of tangent of x over x, because we're approaching 0. And just to review, they're both 1. All right, so I want to know now what f prime of 7 pi 6 is. Let's go to 7 pi 6 on the blue graph. 7 pi 6 on the unit circle is in quadrant what? 3. So it's going to be just past pi. It's about right here. There's 7 pi 6. So if I come down, there it is. If I sketch it, there it is. I'm expecting the slope to be negative, right? And should it be bigger than 1 or less than 1, the magnitude? Should be less than 1. So 1/2-ish? I don't know. I do know it's going to be negative and it's going to be flat. Well, let's see. F prime of 7 pi 6 is just going to be the derivative of sine of 7 pi 6, right? What is the derivative? I almost plugged it into sine. It's cosine, yeah. Now, again, you can work straight down without equal signs, or you can work left to right. So if that is already given, if you want to work left to right, you only do that once, and then you work down. Either way, what is cosine of 7 pi 6? Negative square root of 3 over 2. Yeah. So it wasn't negative 1/2. It was negative. But now I know, oh, for sure, it's negative square root of 3 over 2. Got it. Nice. Look at part C. Find all x on the half open interval from 0 inclusive up to 2 pi, where f has horizontal tangents. Now, it didn't say to use calculus for that, right? So let's go ahead and highlight the function that we're looking at, because there's a lot in there. Here's the function we're looking. I don't want to do that. Let's use blue. Here's the graph of sine of x, right? There's part of it, and then here's the other part of it. So we already know from 0 to 2 pi where the graph of sine of x has horizontal tangents, don't we? It's right there and right there. And it occurs at what? Pi halves and 3 pi halves. So I already know the answer. X equals pi halves and 3 pi halves. If you're doing like a test or something, and you can answer the question without using without BOTCing, right? Without busting out the calculus, that's fine. That's legitimate. But let's verify by BOTCing. The derivative again of sine is cosine. And instead of plugging in an x to get a slope, I'm going to set it equal to the value I want. Now, this is where you can actually have two equal signs. When you have a name function and then you're setting it equal to a value, okay? That's okay. And now we solve. We have to solve, you know, you could take the inverse cosine of both sides if you want and write this, x equals inverse cosine of 0. But this would be inverse cosine the operation, not inverse cosine the function. So there could be more than one output. So I wouldn't even bother with that. I would just ask yourself, where within one rotation on the unit circle is cosine equal to 0? So now we're on the unit circle. Cosine is equal to 0 at pi halves, yes. And then down here at 3 pi halves, where it's 0, -1. Okay, cosine is 0 when we're on the vertical axis, because that's when it collapses horizontally. So I can just say, oh, pi halves and 3 pi halves. And is that consistent with what we saw on the graph? Yeah, facts. It all works out. It all keeps everything else in check. It all works together. It's amazing how we get the same answer when we do it multiple ways, because it works. We've decoded the universe, and now we're using its language. All right, so there's a nice application. I could have you write the equation of a tangent line, you know, and then find its x-intercept or y-intercept, but we'll save that for something that's not so tricky. All right. All right, any questions on 11? Number 11 is over. All right, so here's a nice application of the power rule for which Newton would be proud. Motion. We're going to study particle motion twice this year, actually 3 times, okay? So here's what we know about the derivative again. The slope of the tangent line at the point is equal to the derivative. That's the Leibnizian perspective. But the instantaneous rate of change at that point, that's the Newtonian perspective. 2 dudes trying to solve 2 different problems, ends up being the same problem. Discover the math that is the key to answering those questions roughly the same time in different parts of the world. Pretty fascinating. And of course, now I know that Thomas Jefferson was a fan of Newton, thanks to Jensen. Jensen went to Monticello and took a picture inside Thomas Jefferson's bathroom, and right above his toilet, he had a picture of Isaac Newton. Was that it? Yeah, somewhere in there. Yeah, John Locke, Isaac Newton, and Kevin Bacon. Yeah. But it wasn't in his bathroom. It was in his where? Like in his study or something, his bedroom. Yeah. And it wasn't Kevin Bacon. It was Roger Bacon or whatever. What's the guy? Nathaniel Bacon? Yeah. Shaken and Bacon? I don't know. Advisory's over. Yeah. I have a picture in my bedroom of John Wayne and John Wayne and Abraham Lincoln. So some people will be touring my house and telling their classes. Yeah. Yeah, if she wants to pass it around, it's a real thing. Oh, nice. All right, here we go. If we let h of t be the position as a function of time, h of t is what we use. Sometimes we use x of t if it's horizontal motion. Sometimes we use y of t for position if it's vertical position. Sometimes we use s of t for just position in general, because s, if you say position, you can really hear the s in there, right? Position. That's why we use s a lot. Have y'all seen s for like position or distance before? You know why? It comes from the Greek standard of measure. They didn't use miles. They used stadia. That was their unit of measure for large distances. It was equivalent roughly to our mile. It was smaller or shorter, I'm not sure which, but question, stretching? Stretching. This is where the term stadium comes from as well, okay? So S for stadia, that's where it comes from, all right? But in this case, we're using H. H is another good value to use when you're talking about vertical position that's not up and down on the y-axis, but maybe out, you know, on the football field. You throw something into the air and you're measuring its position above ground. We call that the what? H for happy? Yeah, maybe. H for height. There you go. Did you know that height is a strange word? Because it's okay to spell it either way. Either way is correct. Yeah, I used to say height for the longest time, heights with the TH at the end. And my wife said, you're saying it wrong. And so she converted, I say height now, but they're both correct. Okay, they're actually, like judgment, I do still sometimes when I'm not around my wife. Judgment is another word. It can be spelled with or without the E in the middle. Okay, just so you know. They're both acceptable. Our language, like math, is evolutionary, right? Things change. If we can learn how to communicate better, more efficiently, so that we're not as easily misunderstood, then yeah, then that's we're trying to become that. We're trying to become more efficient. All right. So anyway, here we go. Let h of t represent the height or the position function as a function of time. Let v of t be the velocity, and let a of t be the acceleration. We can relate those three kinematic equations together in the following way. Okay. The derivative of velocity is acceleration. Okay, that is the rate of change of velocity is acceleration, whether it's instantaneous or average. When you talk about how fast someone's velocity is changing, ooh, look at his velocity increase. He is accelerating. Yeah. So whether it's average or instantaneous, the rate of change of velocity is acceleration, but it's powerful when you can do instantaneous. The instantaneous rate of change of velocity is instantaneous acceleration. We don't have to say instantaneous every time. You know why? When I say v prime of t, the of t means at that instant, at that moment in time. So it's understood. So that's the derivative. And of course, the instantaneous rate of change of position is velocity. Wow, look at his position change rapidly, right? He's got some speed going on there. Speed is non-directional, velocity is directional. And so, by the transitive property, if you will, if the rate of change of velocity is acceleration and the rate of change of height or position is velocity, then the second rate of change of position is acceleration. And again, we use this notation here to denote the second derivative, right? I've talked about it. It would be h double prime. So if you memorize your kinematic equations in physics, like if you were told to memorize them, now that you know the power rule, you don't have to memorize them. Memorize them. The height of an object at or near the surface of the earth is measured by -1/2 little g t squared plus v sub o t plus h sub o, or something to that effect. Okay? Yeah, remember that? Yeah, that's from physics, right? And that just looks gross. Okay? Little g is your gravitational constant. It's your acceleration due to gravity, which Galileo knew empirically. V sub o is your initial velocity. It could be a velocity you're throwing it up with or down with, positive or negative, and h sub o is your initial height. Okay? You don't need to memorize the other two equations if you know the power rule, because watch. H prime of t is v of t, and let's take the derivative using the power rule. Multiply and subtract. What's 2 times -1 g, or just negative g, t to the first, plus, what's the derivative of v sub o t to the first? V sub o, right? It's linear, so the coefficient is its derivative. And what's the derivative of h sub o? 0. So there is your velocity equation. Little g is still the gravitational constant. Now watch this. The derivative of velocity is the acceleration, instantaneous, which is also the second derivative of the position. Let's take the derivative one more time. What would be the derivative of negative gt? Negative g plus, what's the derivative of v sub o, the constant? 0. And there you go. The acceleration of a falling object at or near the surface of the earth is negative little g, the constant, which is like 32 feet per second, or 9.8 meters per second. Okay, so we can actually get the three kinematic equations. If we know the first, we can get the kinematic equations this way by using the power rule. But you know how these equations came into existence? They came into existence that way, backwards. Okay, the world runs on what's called differential equations. Solving a differential equations means untaking the derivative. We call that integration later. Okay, so when you go backwards, we start with a gravitational constant that we can measure. We can observe this and measure it, how fast things fall because of the Earth's gravity. Then we can anti-differentiate, which it's also called, go backwards, integrate or anti-differentiate to get this. And then I anti-differentiate or underderivativate again to get the original. So the world again runs on differential equations. Differential equations, when you solve them, means going backwards, anti-differentiating to get the original equation. All right, it's pretty cool. Yeah. So like if you go on to take higher level calculus, it depends where you go, but like Cal 1, Cal 2, like at A&M for engineering, there's a Cal 3, and then the capstone calculus course is called Diff-EQ. Right? You might have heard that. It's short for differential equations. And you're using all of your calculus to solve these differential equations, to undifferentiate things, okay? But if you're not going into engineering, then sometimes Cal 3 is Diff-EQ. Okay, a cab driver? Yeah. All right. Sparkling conversation when you talk about differential. We're going to study differential equations a little bit in here, real basic ones, okay? But there's all kinds of ways to solve differential equation. You have what's called like a Laplace transformation where you turn it into something that looks entirely different. It's pretty cool. It's a fun class, but it uses every calculus little tidbit that you've ever learned. And it's a lot of memorizing too, a lot of memorizing of forms. But anyway, let's take a little example. Let's try it out here. A calculus textbook is stolen from a museum, right? Which is, aside from my bookshelf up here, is one of the few places you can still go to find a calculus textbook, right? Because everything's online now or in this little iPad. So anyway, who would do such a dastardly thing? I don't know. Maybe on TikTok there was like a challenge, right? Go steal a calculus textbook from a museum. Maybe so. Now here's what they're going to do. They take it to the top of a 400-foot tower, and they're going to be dropping it down just to hear it splat below. They're not. Now they're not necessarily a calculus hater, because if they're a hater, they might go to the top of the 400-foot tower and either throw it up higher to give it more velocity on the way down, or throw it down with an initial velocity. These folks are not doing either. These people are just dropping it straight from the 400 feet, okay? So no initial velocity. Its height h of t above ground at any time t seconds. So now we have units, feet and seconds, during its brief but painful plummet to earth. Some people say it's not the fall that hurts you, it's the stop at the end. But this book is cognizant, and it's hurting on the way down. That's why it says the painful plummet. It's hurting on the way down. It doesn't want to be there. It's sad that it was stolen. It's given by this equation here. Now, I didn't have to give you that equation because here's why. We could plug it in over here. In this case, little g, since we're talking about feet and seconds, would be 32 feet per second squared. So I could plug that in here. What's 32 times negative half? Negative 16, right? So that's where that negative 16 comes from. They're not throwing it up or down with an initial velocity, so they're just dropping it. So the initial velocity is 0, so that term goes away. And they're dropping it from a 400-foot tower, so that's your initial height. So you could actually, if you know this kinematic formula, you could create your own equation. That's not going to be an AP calculus thing or a thing in here. I'm not going to make you generate your own equations. I'll give you one of them, and then for now, you're going to take the derivative going forward, but later on, I'll give you the bottom one, and you'll actually go backwards, okay? So here it is. H of t is negative 16t squared plus 400. Answer the following questions regarding the book, right? For how many actual seconds was the book falling, okay? Well, how are we going to figure that out? Ask the book. Solve for t. What's there to solve for? So like solve it, would leave h of t there and solve for t? Set it equal to what? 0. There you go. We have to know something about the book. So how long did it take for the book to fall? Well, what do we know? When the book is done falling and it's laying on the ground, we know its height is 0. So you always have to show the equation that you're solving. You can either say h of t equals 0, which would earn you a check, or you could just say, well, that's not going to do me any good because I have to manipulate it without a calculator. So you can actually set the expression equal to 0. Either way. Or you could do both, whatever. But you have to show the equation you're solving, right? Always. You always have to show the equation you're solving. Now here, you know, you could bring, I'm going to bring the 16t squared across because I don't like negative numbers. And now when I divide through, I'll do the double flipperoonie. So I get 400 over 16. And now a new column. When I take the square root, I have to at least consider what? Plus or minus. I have to at least consider plus or minus. Now, we're talking about time since the book's been falling. Does the negative value make any sense here? No, it's not in our relevant domain. Now, here's the deal. You don't want to just throw negative t values out of hand, throw them out of hand. You want to carefully consider because some activity could have been in the process before we got there with our timer and started it at 0. And now a negative t value can extrapolate backwards to what was happening before. But in this case, it's like, hey, you ready? I'm ready. Okay, I'm going to start the timer as soon as you drop. Okay, 1, 2, ready, go. So negative t values don't make sense. So we've considered them, right? And now we're going to throw it out. So we really just want the positive square root in this case. And look, those are both perfect squares, aren't they? The square root of 400 is 20, and the square root of 16 is 4. And you could have divided first, but I didn't know what 400 divided by 16 was. 20 divided by 4 is 5. So I guess 40 divided by 16 was 25. Who knew? I didn't. Now I do. Now, on your final answer, on any application, on your final answer, you better put units if there are units, or you can lose a check. We're talking about t, so that is t in what? Seconds. So there you go. So from 400 feet, if you let it go, and of course, neglecting air resistance and a bird coming by and knocking it off course, everything falls at the same rate, right? Galileo proved that, neglecting air resistance. So anything from 400 feet would take 5 seconds to fall. 5 seconds. That's a long time. That's a long time to feel the pain of, why did they take me out of my museum? Why am I not in a calculus room anymore? I hate technology. Maybe this is good for me. I'm not needed anymore after all. Acceptance. 5 seconds is a long time. Now, how many seconds did it feel like to the book? 100 seconds, 2 seconds. Some people, that you're not going to be asked that question. That's just that'd be like in a creative writing class, right? It felt like an eternity, right? The book was left with its thoughts, and his mind raced, you know, it's all over the place. His life flashed before him, and he relived every single moment in those brief 5 seconds. Felt like it felt like a second, right? He didn't even have time to react. He was like, what's happening? Well, so anyway, we're going to answer objectively. We're going to answer numerically. We're not going to get into that fuzzy questions at the end. What was the velocity of the book in feet per second the instant it hit the pavement? My favorite answer to that is 0, right? When it hits the pavement, it's not moving, 0. That would be in the very next instant after it hit. I want to know as it hits, at that moment, how fast is it going, right? I need to figure out the instantaneous rate of change of height, therefore its velocity at a single moment in time. That's the derivative, isn't it? I need the derivative. So here we go. H prime of t is v of t. It's a function, velocity function at t equals t. That's instantaneous. By the power rule, I take the derivative of negative 16t squared, and I get negative 32t. So I'll bring that down here. And then the derivative of 400? 0. Yeah. Now, what value of t am I going to plug in? Do I know the time value for? We just figured that out. And that's a very typical thing that College Board will do on like a free response question. They'll have you find information that you'll need later on. So now I'm going to show it. Since I've called h prime of t v of t, I don't need to keep using both. You can, but I'm just going to use v of 5 now, which is negative 32 times 5. And that gives us negative 160. And on our final answer, we put units, right? I'm going to put the 5 in parentheses. I don't like it. It looks like a decimal. Feet per second. Right, there you go. Now, you don't even have to even introduce v of t into this. You could just use h prime of t the whole time. But when we do motion problems, you'll see that I will always encourage you to make that connection. So always call h prime of t v of t. Always call v prime of t a of t. Okay. What you do have to do for sure is when you switch from a variable to a number, you have to show that on both sides. Okay. Yeah, the negative doesn't mean that the book is falling upside down or backwards. It means that the height is decreasing, right? It is literally the rate of change of the book's height. And the book's height is decreasing, right? Why is the book's height decreasing? It's falling. Yeah. Let's go ahead and write a sentence. We haven't really done this yet, and there's a whole time to write sentences later on, but now's a good time to throw it at you. You might be asked to explain the meaning of this in the context of the problem. And when you have velocity, there's kind of two ways to do it. If it says in terms of the book's height, there's two ways to do it. In terms of the book's height, here's what it would be. At t equals 5 seconds, you're always going to answer with the independent variable, with units. So that's the first thing we did when we evaluated, right? We plugged in the 5. I call that the introductory adverbial clause. That's what it is. At t equals 5 seconds, comma, we need to talk about the height, okay? The book's height, try not to use the passive voice. It saves letters. The book's height is, do we say changing at negative 160, or is there a better way to say that? The book's height is, I wouldn't say the book's height is falling, but how about increasing or decreasing, right? The book's height is decreasing. Now, that's the engineer. You'll hear me say this a lot. This is the engineer way to answer it. It's really straightforward, okay? It checks all the boxes. You're going to get full credit. If you want to take it to like a wordsmith, like an English teacher, they might just say, when you say the height is decreasing, you could just say is falling, right? And that's fine. Sometimes you might be able to use like better words, but if you always talk about a quantity increasing or a quantity decreasing, you'll always get full credit. You can leave the rephrasing to another day, right? To another profession or to another hobby of yours. So at t equals 5 seconds, the book height is decreasing. You could just say by. You don't have to say at a rate of. By kind of is a really nice word. By positive 160 feet each second. So in your sentence, you're always going to want to expand out the units and write them in words. And you could have said feet per second or feet every second. I just like to switch words there because it's a deliberate thing. You don't want to put FT/SEC in your sentence, okay? Now notice I didn't put negative 160 in my sentence either. Why not? I already said it's decreasing. So when you write your sentence, you're basically interpreting the answer as a vector. It is a vector. It's a direction downward with a magnitude, a speed. And so you're always going to interpret it in its two parts, the speed or the magnitude, and then the sign is increasing or decreasing. Now, there's another way to do it. You could also answer the question in terms of the book's velocity. And so now you would say at t equals 5 seconds, comma, the book hits the ground. We'll say the book hits the ground at 160 feet per second. Okay. Notice the difference there. Bless you. I still didn't use negative 160 because I'm talking about hitting the ground. So I'm giving the speed, and the direction is implied there. But notice I didn't spell out feet per second. Why not? What do we measure velocity in? Feet per second. What do we measure height in? Feet, right? So the units of whatever quantity you're describing have to match up. So if you're talking about height, you need to talk about a change in feet or meters. If you're talking about a velocity, you need to be talking about velocity units, which are feet per second. Okay? Not that you'd lose points there if you spelled out feet per second, but you don't need to. All right. Part C. Let's get away from calculus. What was the book's average velocity during its fall? This is the algebraic version now. This is Galileo. Average velocity is different than instantaneous, right? During its free fall. So now we know that the book is falling for the interval from 0 to 5 seconds, yes? So I have an interval. You can write it like this as well. So average velocity, is that going to be v of 5 minus v of 0 over 5 minus 0? Or is it going to be h of 5 minus h of 0 over 5 minus 0? Both of these are the difference quotient. Whenever it says average, in this case, it's the difference quotient. Which one do I use? Change in v over change in time, or change in h over change in time for average velocity? When in doubt, look at the units. Average velocity should be measured in what? Feet per second. Right. If I look at the units of the second one, height is measured in feet, time is measured in seconds. That's going to give me feet per second. If I do the change in velocity over change in time, that's going to be units of feet per second. That's going to give you not the average velocity, but the average what? The average acceleration, right? Okay. So remember that before calculus, people couldn't even figure out the velocity equation from the height equation. So they didn't even, doing the first one wasn't even an option. So we're going to do the change in height. So what was the height at 5? It was 0, right? It hit the ground. Minus, what was the initial height at 0? 400. What was the change? 5, right? So if we calculate that, we get negative 400/5, which is negative 80 feet per second. Now here's an interesting question. Was the book falling at 80 feet per second the entire time? No. It started going 0 feet per second, and it ended going 160 feet per second. Did there have to be a moment in time between the start and the end where the book was actually going 80 feet per second? Very good. We're doing the IVT now on the derivative, aren't we? On the rate of change. When you do the IVT on the derivative, it's not called the IVT, it's called the MVT, right? Because we're talking about speeds now instead of positions. But we'll get to that later. But yeah, it's the same idea. You can't go from 0 feet per second to 160 feet per second through a continuum without passing through 80 feet per second. Okay? It just makes good for your response question. All right. And then what was the acceleration of the book in feet per second during its fall? Notice it didn't specify it didn't time. It didn't specify a time at all. Well, if I figured out the average acceleration, I don't know if that would give it to me. Would it? V of 5 minus V of 0? Can I find the acceleration at any given moment? Yeah, what would that be? That would be the derivative, right? Yeah, so let's rewrite V of t, or h prime of t if you didn't call it V of t. It was negative 32t. If I take the derivative of that, I'm going to call that a of t. What's the derivative of negative 32t? Negative 32. It's a constant. Is that my answer? Do I put feet per second on the end? Well, if you leave it like that, you're calling it just the function at any given time. But you know, since there's nothing to plug into, that is the answer. So what you do want to just say is the book's acceleration I'm just going to say was, I'm not going to interpret it, was negative 32 feet per second squared during its fall. And then I'm going to say right here in parentheses, go gravity. We would expect that. 32 is about 9.8 times 3. 9.8 meters is about 32 feet. Okay. So whether you're talking about meters per second squared in physics or 32 feet per second here, it's really the same idea. It's an empirical value. Now, let's write another sentence, because you can actually just talk about the acceleration being negative 32. But acceleration is the rate of change of velocity, right? So here's another sentence we could say. During its 5-second fall, comma, the book's, there's your antecedent, right? The book's velocity was whating? Increasing or decreasing? The speed was increasing, but the velocity had to be whating? Look at the derivative. It's a negative number, isn't it? If the acceleration is the rate of change of velocity and it's negative, the book's velocity was decreasing. Yeah. By, and here's how we're going to answer it, 32 feet per second each second, or per second, or every second. But notice, again, because I'm talking about velocity, I answer it in velocity units, and then every second. Yeah, now, the speed was increasing, but velocity was decreasing. Why is that? Velocity is negative here, and so is acceleration. When you have velocity and acceleration working together, the same sign, it's like running with a tailwind. You're going to speed up. If velocity and acceleration are working against each other, opposite signs, it's like running into a headwind. You're going to slow down. Okay? So when we talk about speed, later on, we're going to be comparing the sign of acceleration and velocity at that moment. In this case, because they're both negative, the speed is increasing, okay? But the velocity itself is decreasing because acceleration is negative. So getting velocity and speed straight in your head, kind of an important thing. Have a fantastic lunch. We finished just in time. Oh, I know Justin. He's a nice